Thank you very much for the introduction. The work I'm presenting today is based on my bachelor's thesis, which I did last year at Saarland University in the group of Gerd Smolka, supervised by Dominik Kirst and Yannick Forster from INUA. They are also both here today. And let's jump right in and clarify some of the technical terms in the introduction. I think it's working. What is a probability predicate? Sufficiently strong formal systems S, for instance, piano arithmetic, or most of the type theories presented here at this conference, have these probability predicates. And this is a formula in the system that has one variable that characterizes the probability of other formulas in the system, in the sense that some formula phi is provable in S if and only if this PR instantiated to some encoding of phi is provable in S. Seems quite simple, but in fact, it's quite technical because there are many different probability predicates of various strengths, even for the same formal system. They may all satisfy this equivalence here, but what you can say about them on the object level may be substantially different. And this is something also we run into while working on this project. Are they interesting? Yes, they are. They give rise to really interesting results. For instance, Gödel's incompleteness theorem. It's good to find out that if you've got a formal system and a probability predicate that are strong enough, then he constructed the sentence phi that is on the object level equivalent to its own unprovability. And he found out that these sentences exist and that they are independent, giving rise to incompleteness. A couple of decades later, Henkin asked a similar question. He constructed sentences phi that are equivalent to their probabilities, where he dropped this negation. And he wanted to figure out what happens to these sentences. And then in 1955, Loeb answers Henkin's question and found out that if you've got this formal system and a probability predicate that's strong enough, and you've got some sentence that satisfies this equivalence from Henkin, the existence of these sentences is clear, then you essentially have that S proves phi. And with this, we are in the position to state Loeb's theorem formally. What does it say? If you've got a formal system S and the probability predicate for it, and both are sufficiently strong, then in order to prove a sentence phi in the system, you can assume on the object level that the sentence is already provable. Sounds a bit contradictory or even absurd. To prove something, you can assume that it's provable. And in fact, it's quite difficult to digest. But Loeb's theorem is interesting in various ways, because first it gives rise to interesting results. It implies Gödel's second incompleteness theorem if you instantiate it to the bottom, to the falsity bottom, to the formula bottom. It's also interesting from a mechanization perspective, because there's only one mechanization of the second incompleteness theorem, which is to Paulsen from 10 years ago and Isabel. And to do this mechanization, he had to mechanize extremely tedious technical details. And Paulsen proofs easily extends to Loeb's theorem. We did this as part of our thesis. So at the moment, there's only one real proof of Loeb's theorem from first principles in some system of logic. On the other hand, the first incompleteness theorem, which is a bit related but still quite different from how to prove it, has been mechanized a couple of times. And one mechanization, which is particularly interesting, is due to Kirst and Peters, which was also presented at TYPES2025 and CSL23. It's a computation proof of the first theorem that uses synthetic computability theory and an axiom called Church thesis, to which I'll come back later. And it's based on work by Klemyshev and textbook proofs Pliny. And they leave the second theorem as future work, and that's where my work began. That's what's the question? We wanted to find out whether there's a less tedious proof of Loeb's theorem in the spirit of what Kirst and Peters have done for the first theorem. And Loeb's theorem is not only some abstract thing in logic; it's also interesting to the types community. When you get to things like self-interpreter, self-reference, rotation, Loeb's theorem shows up quite often, or Loeb-like structures show up quite often. Gauss-Gallacher and Feinstein did some analysis of this in ACTA with type theory. And it's historically known to have an intricate proof. And many known proof techniques are known to fail, so it's really hard to get Loeb's theorem. And we wanted to figure out whether there's a synthetic perspective that simplifies arguments. Why is a synthetic perspective interesting? Well, usually technically integrate details vanish, and you can focus on the meat of the argument. So all the routine verification goes away, and you can focus on the interesting part of the proof, the meat. So you get 90% shorter proofs, and the 10% that remain is the interesting meat. Well, I've said sufficiently strong a couple of times. What does that actually mean? I think that's the most technical thing you will see today. Sufficiently strong comes in two ways. once for the probability predicate, we require that it satisfies some conditions known as the Hilbert-Bellner loop conditions. There are 3 of them. The first is something that we've already seen. It's necessitation. It says if you prove the formula phi, then you can also prove the probability predicate instantiated to phi. It's something that we've seen on the first slide already, but for historical reasons, it's also part of the HBA conditions. Then there's the distributivity law. It says that the probability predicate knows how the modus ponens rule works. You've got the implication and the premise, you got the conclusion. It says that the probability predicate knows how to prove. The first one is, and it's a bit technical, you don't have to parse or understand it, but this is the most tedious to prove actually. In most cases, it's if a formula is provable, then it is provable, that is provable, and this implication here is in the object. For theories, we require the diagonalization property. Actually, quite a nice thing. The diagonalization property says that if you've got a formula phi in one free variable, you can find a sentence G, a closed formula, that is on the object level equivalent to phi instantiated to some encoding of G. And we've seen on the first slide a couple of these things where you've got some equivalence in this way, and that's in fact the key ingredient to get these sentences. That's also what Gödel used in his proofs. And from HBL and the Dirac property, you get Löb's theorem via short and abstract argument that doesn't have any intricate details. We wanted to approach Löb's theorem in using the way Kirst and Peters did. So what did they do? Well, one of the key ingredients that we use is the axiom Church thesis. And it's a nice thing. It's an axiom in constructive mathematics stating that every function is computable in a concrete model of computation, or phrased a bit differently. In a constructive setting, you've got a quantifier, all quantifier over formula over functions, then this quantifier only ranges over computable. And the results that we recognized are based on a variant for Church thesis for arithmetic. And how does that look like? Seems a bit technical. We've got for all f, we got all quantifier, all functions on the natural numbers, and then it's computable in some setting. In this sense, in Peano arithmetic, we get a formula phi f in Peano arithmetic that internalizes the computation of f. So whenever you got some natural number n, and you plug in this n overline is a numeral representing n, so it's a term representing the number n, and whenever you plug any other term y in it, this formula phi f is provable if and only if this y is in fact the term representing the numeral of f of n. So phi f internalizes the computation of f in Peano arithmetic. And the nice thing is that it is consistent for the calculus of inductive constructions, which we've used for the Rocq mechanization. It's not consistent for Isabel. It's a small part where we extended Paulson proof, but there's not a problem because the Isabel mechanization is free of any axioms. Church thesis is only for Rocq. There we can assume that it's easy and it's nice. How can we exploit Church thesis? Well, we get a provability predicate. Provability in Peano arithmetic is enumerable, and then we can throw in the enumerator into Church thesis and fiddle a bit around with the formulas, fiddle a bit around with the formula that we get, and then we get a probability predicate in the sense I've mentioned on the first slide. Also, we get the diagonalization property. It's the diagonal lemma that essentially states that we get the diagonalization property for Peano arithmetic. And this gives rise to the first incompleteness theorem, Tarski's theorem, essential undecidability of Peano arithmetic, all nice results, but unfortunately, we don't get Löb's theorem. And the problem is that all that we know about the probability predicate is that it satisfies this equivalence thing. But there's no way, and even there are probability predicates that satisfy this equivalence here, but for which one of the HBA conditions fails. And Church thesis is not strong enough to tell us anything about it. And there's the internal versus external probability. External probability is only having this equivalence here, and CT gives us these things. But internal probability is much, much stronger and requires insights into the system, and CT doesn't give us this. And it was really hard work to figure that out. We spent lots of time on getting to understand this. Still, can we still define probability predicates? Yes, of course, we tried. Proof, how did Gödel do this? Well, the proof is encoded as a list of formulas. And then he encoded all the required lists and syntax functions in arithmetic. Extremely tedious stuff, but you can do it. Well, Peano arithmetic is not a nice system for this. So we extend Peano arithmetic by list functions, near and cons, new symbols, to make working with lists easier. We get a length function, we get an index access function, all the standard functional programming stuff. We have an append function, and we've got an implication function. This is just a syntax function. If you give it two encodings of formulas, it spits out the encoding of a formula representing the implication. And based on such a definition, we, in fact, defined a candidate for an internal probability predicate, so the ones that are strong enough for the, and we mechanized two of the three HBA conditions. and I'll talk about the last one later. But let's first highlight what we've done as part of our work. Well, we wanted to figure out whether there's a proof of Lip's theorem with synthetic computability church thesis. Unfortunately, there's no such proof. I can't do it. These things don't give enough insights into the system. Lip's theorem is too deep for this. We mechanized Lip's theorem twice, once in Rocq, where we assumed that the H48 conditions hold, and where we assumed church thesis. From this, we get Lip's theorem, and also in Isabelle, based on Paulson's development, and this is completely free of any axioms. Paulson proves all the hard stuff already, lots of code, but our proof is only a small extension. We mechanize the diagonal lemma and the key limitative theorems, Gödel 1, Tarski, and so forth, assuming church thesis. We analyze why church thesis is doesn't give us deep enough insights for Lip. And we recognize an extension of pair arithmetic, making the internal probability predicate definition easier. And we gave a candidate for such a predicate and mechanize some of the correctness proof. Well, we mechanize some of it. We want to finish mechanizing the proof. We want to mechanize this last one, internal necessitation. And for this, we may need to extend the system even further to we may need to add more syntax functions, just technical stuff, but it's really hard work. We also like to contribute the Isabelle proof to the archival formal proofs. This is already underway. It's been submitted, but the decision is pending. We also like to contribute the Rocq development to the Rocq library of first-order logic. This is also already underway. And we would like to mechanize an axiom-free proof of the diagonal lemma and limitative theorems, see how important church thesis actually is, how many technical stuff is avoided by church thesis, and we would like to investigate this. And with this, thank you very much, and I'm looking forward to the discussion.